So I'd like to welcome everyone to our May meeting of the Melbourne ATA Electric Vehicle Branch. Thank you all for coming out on this cold night on those, so coming out to see us. We've got a few good things to show you tonight on those. We've got Aerochute talking about their electric parachute design, what they've been working on, as well as a few other projects and some other things that are going on within the ATA branch. So thank you for coming along on those, to see you. The first thing I wanted to talk about today was the expo, which we had in April. It's just on a month ago now. We're really pleased with how it went. We had a really good turnout. We had probably over 3,000 people coming through, which was pretty much double what we had last year on those. And I think a lot of work went in for the committee and that in setting it up. And the ATA did more work on the expo this year. But I just wanted to show you through some pictures, first of all, of the expo on those, for those who didn't manage to go along. Those, but we had the expo through there. So plenty there. It's a good day. We've got the BMW. This one's the old car. Remember what it's called? Detroit Electric. Yep. This bike won the show and shine. There's Mario's EV Capri. We got here a Volt. At least the rain did stop in the afternoon, so people were able to go out and have a look around. It's a bit wet in the morning, wet and cold. Nissan were there. Still a few umbrellas out. And then inside in the atrium area here, we had a lot of the different stalls. This is the Suzuki, which is done by the Geelong branch on those, putting that together. Barjar board, developing this electric skateboard. And a nice bamboo bike by Rev. Hard to find room for everyone at that time. It's certainly crowding in. Some of the stalls inside, Enviro shop. Yeah, even get in there with a just disability access. It's the ATA, RACV, both sponsors of the event. Zero Motorcycles, they were there.
That's when the sun came out.
Yes, in the afternoon, in fact, it came out. Someone making use of the test drive, the bike ride track. Dyson bikes, one of the e-bike suppliers were there. We have a lecture theatre with Dean up on front, doing what he does best, chatting to them all about, I think he was introducing that. It says Fonzarello scooters. Fonzarello, another scooter manufacturer. The Zeros again. There's Swinburne's little racing car. Then Aurora and their solar. BMW, that'd be the i8, would it? Yes. The i3, the i8. Our shop has a Tesla. Here's the Detroit. I really especially like the vase that was in the side, you know, the vase with the flowers. You put in a car. It was like sitting in a lounge suite. Justin's Mitsubishi, little green Kermit, something from the 70s. Anyway, so we're very pleased with how it went last year. Planning's already well underway for next year. And those, we set a date in, is it March? Yes, March the 20th on those. We've got as a tentative date, but we're pretty sure that's going to be set on those. So we've already started planning for next year. Anyway, so that was the EV Expo. So I was just asking, are there any members' projects going at the moment? Any of the members up to doing anything in the EV area? Or if you got any news about events that you might know coming up, whatever?
Actually not a member, but I have an EV project that's near completion. Probably might remember from a few months ago, pretty busy being overseas, but I'm back. I'm actually going to leave the country in about 2 months, so haven't had much interest yet. Cancel your visa. No time to get finished, but yeah, the price is dropping every day, so if anyone wants to pick up a
what was it? Was it the Toyota Yaris? Or was it?
Yeah, the Toyota Echo 2004.
Echo. AC,
brushless and lithium, and it's all high-end stuff in there. Now, the only offers I've had are like vultures circling for scraps. Like, I'd really be interested in someone taking on the whole project, taking it through to completion rather than splitting it up apart.
Oh, okay, so that's yeah, so that's a Toyota Echo. That's partly through building. Yeah, on those four really components.
Drive it around. It's even still registered as an ICE, which apparently was a mistake. But someone told me at one point that it was best to keep it registered throughout the project. So
okay, so there's a project that's been interested into going. So if anyone's interested in the Echo, you said it was Toyota Echo on those converted to electric. What's your name?
eBay soon, Mark.
To let Mark know.
I'll make offers at the end, but I'll probably just put it on eBay and let people find it out on there. So.
Well, that's right. And also all the members in the group, if someone's interested in it, they can also buy it off eBay if it's gone on eBay. And that's so you get a wider range of interest.
I'll grab a bargain.
Okay, Eleanor, what did you want to say?
I'm just trying to actually I'm still working on our project, although it has temporarily stalled due to lack of funding. But we're still taking away there.
Yeah, I remember I talked to Eleanor last month on those. She's working on a velomobile on those for yourself, isn't it? So four-wheel, you want to do a four-wheel velomobile?
Yes, exactly.
On those, so that's a project that they're working on those. They're good friends of Dean and Rebecca, and those are red bikes. So there'll be a few people that'll be working together to try and put that project together. Anything else? Yes.
My name's Tim Isaacson. I'm currently involved in a EV advocacy project. I'm actually putting up, I've been putting up a series, thanks to Mario and others who I met on the day at the EV Expo. I've put up a series of, to date, 3 videos of 2 minutes each related to the Expo, which are interviews and cutaway material that's been shot since. The first one was everybody at the Expo talking about their vehicles, and it is on YouTube. It features the ATA and the EV logos. The second one was on Mario and his Cabriolet, and the third one went up a couple of weeks ago with John and his Leaf. He was also there, and the next one going up will be, which will go up tomorrow, will be a guy called Chris McIntyre and his electric utility vehicle that's made in Italy and is used as a city utility rubbish truck. The ones that will be going up subsequent and following on from that will be Kerry and her Outlander, Kerry Hill and her Outlander. Then I think it's going to be Rolf and his Bolt, and then I believe the one after that will probably be Costa and his Unos. I'm on the lookout to catch up with Michael to do the iMove, and if anyone else has EV vehicles that they would be interested in featuring in a 2-minute video on YouTube, that would feature the ATA EV logos and probably RACV and Buradara logos, as well as promoting next year's expo without actually pointing to it, but using this year's artwork. Come and see me.
Okay, so if anyone else has a vehicle that they want to have a little 2-minute presentation and that done on those, to come and see you.
Possibly before the end of the meeting, you might want to play the 4 that exist. I've handed them to Adrian and he can have a peek at them.
Oh, thanks. Yeah, we'll put those up and play them. And thanks, we've also put a couple of them up on the EV group page, on our Facebook page. Thank you for that. And those, so yes, to see something like that come out of the expo on those and see someone who can create a few short videos on those that'll just show what electric vehicles are doing and probably what each individual person, you know, they own the electric vehicle and what they do with it and how they feel about how their vehicle's going on those and as they use it. Thank you for doing that. Is there any other news you wanted to bring up? Okay. Well, with the EV group here, we're looking at starting a new project on those. So before we do the Aerochute presentation, I just wanted to do a short PowerPoint on those on a project that we're looking on, which is to do with charging. Okay, thanks. So this little PowerPoint's on fast charging in Melbourne. And those, so the fast charging stations, you can see here we've got a Swinburne fast charging station. Melbourne now has 3 fast charging stations. A 3rd fast charging station has just been started here in Notting Hill. So now we've got an area there that's covered with fast charging stations. So the fast charging stations enable you to pull in, charge your vehicle up quickly on those and then drive away. Next one. So why fast charging? Well, most people with electric vehicles charge at home because it's usually overnight. It's very convenient in that to charge at home. The electric vehicles have a range of 100, 150 kilometres on those. So generally you can do your trip on those from your charging at home. But with a fast charger, you can travel further in a day. So people will be able to come into Melbourne and those and be able to, once they arrive in the suburbs area, do a fast charge and then do their travelling, whatever they need to do around the suburbs. Or maybe they might need it to make their way back home again if they live out of the Melbourne area. It enables you to travel further in a day. And then there's always the fear, oh, what's going to happen if I run out? So there's the guy there pushing his smart EV on those. So with a fast charging station, you've got the security of knowing there that there's somewhere that you can go where you can charge your car rapidly on those in half an hour or so, and those to be able to get home. The next one. So the fast charging stations work on the CHAdeMO protocol. So this is one of 3 different fast charging networks that are available. Those 3 stations here in Melbourne are all CHAdeMO. The CHAdeMO charges to 80% in 30 minutes. So it uses a DC charging system on those to charge the car up. The actual charge is not in the car, it's in the charging station. So it's providing direct current that it's already producing to charge the car. And it can therefore charge at a very fast rate because you can put a big charger at the charging station. 50 kilowatts is the rating, but they can charge it up to 450 volt batteries, and CHAdeMO the Australian standard, and those 125 amps is a common standard. Some of them can charge at a higher rate. 125 amps is pretty much what you see in CHAdeMO. So that's the fast charging setups that we have around Melbourne. So CHAdeMO, this is the wiring for CHAdeMO. On the right-hand side here, we see the plugs and the sockets. And the socket through there has 2 main DC pins and then a number of other pins in that around it. But why I'm presenting this to the groups, we're looking at doing a CHAdeMO charging project for electric vehicles here in Melbourne on those. So in developing a CHAdeMO charger that can be put into one of our home-built cars, home-built vehicles as such, so that you'll be able to have access to CHAdeMO charging. With the cars that we build here that different people in that have built, it would then enable them to do a fast charge to be able to travel to the other side of Melbourne, charge and come back, or give a lot more versatility to the vehicles. But this is the connection interface for CHAdeMO. Not very difficult. There's a few connections. We've got our main power lines, DC, that go through, that just connect straight to the battery through a contactor. So that's the main thing that charges the battery. We then have some analog control lines here that tell the charging station that there's a vehicle actually there on those, what we call proximity, and that whether we're to start or stop charging, whether the vehicle's fully charged. On those, these analog control lines enable all that communication with the charging station. And then the last one through here, there's a CAN bus. CAN bus, which is a well-known communication systems, a computer type communication that's used in vehicles as well as other local small area networks. But what the CAN bus does is tell the charger how much current do we want to run into the battery, a bit more information on what the voltage of the battery is, and those. So it needs to communicate with the charging station on CAN bus as to how much charge we want the charging station to produce. So if you activate all those lines on those, you've got your charging station. So the components that be required to build a charger like that, typically Arduino, one of the microprocessor boards, and then it requires a CAN bus shield, which is the communication shield there that operates CAN bus, the communication lines. The battery contactors to turn the power on and off, and then a program to make the whole thing work. So Arduino is called Sketches, but these programs and those are written there so that you get the correct charging currents and the correct cut-off voltages and everything required for your vehicle. So these are some of the things that have to be developed to be able to build a CHAdeMO charger.
Sorry, where do these bits go? In the vehicle?
Yes, these bits go in the vehicle. So this board would have to be in the vehicle next to the charging socket. Any other questions there?
New socket into the vehicle.
Yes, let's go back a couple of slides to with the CHAdeMO socket. Yeah, there it is. This one here is the CHAdeMO socket that would actually go on the vehicle on those, and that's the plug that's on the charging station.
Would you propose that vehicles have 2 charging sockets?
Yes, I would on those. J1772 is a well-known standard for charging. Enables you to charge a vehicle in 2, 5, 6 hours on those, whereas this faster charging socket charges in half an hour. There's a number of the commercial vehicles already available that have this fast charging socket on them, and those, it varies from brand to brand of the commercial vehicles. But we could lead the way with our development of our own built electric vehicles on those that have CHAdeMO charging on them, and make them a lot more versatile. They could be charged quickly. Let's go to the last one. Oh, okay, this one here. There's a difference in the batteries that we're using with some of these electric vehicles that tend to be built at home. They use these LiFePO4 batteries, whereas the commercial vehicles use a different type of battery, either NMC or NCA. The NMCs are used in the Leaf and the Volt, and the NCAs are used in the Tesla Model S on those. So they have a different charging characteristic. So as I've got a little short video, someone who's already over in Ireland has worked out how to do CHAdeMO charging with these LiFePO4 stationary storage batteries. they've worked out how to do it on those, so it's not an impossible project. We know others in that are working on this and have had some success, and that we could also be able to do that, to design a CDMO charger on those from for the electric cars that we build in the club. So in the next one, if you'd like to play the video, let's see if she go.
I had my first successful charge at this SGTE fast charging station. Not at the full 120 amps. My first successful charge was at 60 amps. And with some cold mods then we took that up to the full, we took that up to 90 amps. Still haven't gone to the full 120 that the station reports itself capable of performing. It's just really great to be able to have that facility to fast charge my car, and that's a facility that we're definitely going to be putting into their Panzer, and I'll be probably having to get another CDMO connector for that, and start doing the various wiring up to make that happen. So I'm going to put these clips on, and as always, guys, thanks a lot for watching, and we'll see you all.
Okay, folks, we're back at our CDMO fast charging station, and we are charging again on the Aerochute charger, and hopefully these numbers will come out. We are currently in the tapering stage of the fast charge. So unlike the cells in the OEM vehicles that have a very linear charge curve, the LifeCo 4 cells in the land yacht have a very flat one. So we're basically aiming to hold 175 volts, which is in the blue numbers, and our current is in the red on the right hand side, and we're basically dropping that back from 125, we're now down to 112 on this display here. So I'll come back in a few minutes when we're pretty much down to a full battery. I'm dropping through 45 amps. It's a bit like watching paint dry, but it's just interesting to see it working properly. It's very different charge curve to the NMC cells that are the manganese cells. We will have quite a different response when we work with the Renault Fluence battery for their Panzer. Our software is configured to terminate charge when we hit 10 amps. So far we're pretty much on target to make that happen. I can, of course, at any time press the stop button on the fast charger, which would also terminate charge, but I'm just interested to see it happen automatically here. It'd be very important if I decided to plug the car in and go off to do something.
I like his RS accent. But so there are people working around the world on those on CDMO, and those in developing a simple charging system that can be fitted to a home-built car on those to enable CDMO charging. So my idea for the project, well, I've already ordered this CDMO sockets from China on those, so I've got a couple of them coming in those, and we've been able to source those at a reasonable price on those, not the $300, $400, $500 that I've sometimes seen. And then the Arduino boards, and then the cam capture. So I'm interested in people who'd be interested in coming in and being involved with this project on those, and if they could come and see me, and we'd like to just make it happen. So the charging station that I showed, of course, there was Swinburne on those, the charging station there. So I'm sure that there might be people within the audience here or students out in Swinburne. I haven't really spoken to many people yet about this project, but we're looking for people to come in, partner with it, and see if we can get this project done so that we can have fast charging on that on our vehicles. So that's the CHAdeMO, the fast charging. Okay, also the Melbourne EV Group, on those we've bought some of these little charging reminder that you can put on your car when it's in the charging station on those, because it's quite often happening, people are unplugging. Someone might need a full charge to be able to get home, and then they find out when they come back to the car they've been unplugged. Then on the other side it says okay to unplug, because I'm just opportunity charging. You know, I've come in, I'm at the shopping centre and I see the charging station there, so I'm just plugged in to top my batteries up because it's free at the shopping centre on those, and then they might have that side on there. So these are just little cards that people can buy for their electric vehicle on those, and they can keep one in there and then let people know whether they can unplug them or not after they've finished their charging.
Well, is it a problem that we're actually unplugging other people's cars with them anyway? It's a no problem?
Yes, yes it is. I know.
So they're not trying to create anything like a mechanical lock or something to do that, because I mean, I'm not sure how many people can expect to sign on it anyway if they're going to do that in some cases.
Well, a charging station might quite often be near two parking bays on those. So when someone comes into the second parking bay and they see someone's already plugged in, you know, they might think, well, I need to charge my car. I've got to be able to get home on those, and they might think, well, maybe he's finished, you know, and they'll unplug him, or maybe he's opportunity charging like that on those. So yes, it does happen, and it can be very annoying. And of course, what can be even more annoying if there's if there's a petrol car there parked in the EV parking station and you can't plug in at all because someone's just gone and taken the parking spot and not plugged in at all. But yeah, these little cards there, just a little reminder for people to say whether it's safe to unplug your car or not on those. So we'll be selling these at $3 each. So if you've got an electric vehicle on those, so it might be an idea to have one of those in the glove box, and those for when you go charging. And before we have the Aerochute presentation, I just wanted to show a video on those. We like Aerochute, for instance, is something that's a bit different. You know, we're now using batteries in other sorts, like in aeroplanes and things like that. But this one's just a little video on boats. On those, there's a company in Amsterdam that's doing electric speedboats on those, and they've been 2 or 3 years now using high power batteries, AC motors, you know, and creating really exciting boats on those with electric power. So I'll just show this quick video.
Making electric boats isn't just making boats cleaner, it's making boats better. Being out in an electric boat means you can enjoy the environment you're in. You are so much more immersed in the sound and the experience of the aquatic life of the water, of the wind, than you would otherwise be. And it really gives you a new level of understanding and enjoyment of that generally beautiful nature you've gone into to enjoy yourself. What an electric motor does is that it gives you all this power in a vibrationless, soundless way. A well-thought-out, well-designed system has 100% of the torque available all the time. You don't have to build up to it, you have it. So when you pump the throttle, you are out there and your whole shot is amazing. It takes your center of gravity right out from under you, and it gives people what they call the EV grin. You just start laughing, you can't help it. You're so conditioned to think that you first need vibration, then need noise, and then you start going somewhere. And in this case, your center of gravity just shoots right out from under you. And it's a wonderful feeling. You can still talk to each other and hearing the sound of the water and the wind and the waves instead of just hearing engine noise and vibrations. And it gives you really a chance to be in tune with that nature that you're actually out there to enjoy. Plus, not having to visit the pump is actually a great thing. Your battery will heat electricity from any source that you provide. I mean, we love sitting around on the knees with a jerry can. We have better control over the boat. We have a better experience while we're out driving. Plus, we also have the knowledge that we're part of new technology. It is just way cool. Our mission is to make beautiful, fast, and fun electric boats. There's nothing more fun than taking these new technological developments and putting them into classic designs and having people shoot away with a big smile and an easy grin.
A little bit more. We'll play the next bit, and then it'll stop. Just another minute. There's towing a skier. That's it. Yeah, so electric motors can be used for a number of things, can't they? So you can put them in a boat as well and create some really exciting boats, and that with them, like power boats, speed boats, with them as well. Well, next we've got Clint talking from Aerochute, giving the presentation now on what Aerochute's doing on those with developing their electric prototype. So Clint is a lecturer at Swinburne, so please come up and tell us what they're doing.
Thanks, Rob. You want to press buttons for me, Adrian? We're going to get pulled it up.
No.
Okay, thanks. It's a bit of an awkward setup here. All right, so yeah, as I said, we're looking at the development of an electric aerial vehicle. Specifically, we're looking at an Aerochute, or a powered parafoil, as some people call it. And as you already know, my name's Clint Steele. Okay, so first of all, a bit of background. Aerochute International is where it all started. A lot of people don't know this, but there's a small aeronautical company in the northern suburbs of Melbourne, and it's Aerochute International. And what they actually make are those powered parachutes, or parafoils. And basically their selling point, their major selling point, is the cheapest and easiest way for you to get your pilot's license. I think it's a category D license you get, which is basically one of the cheapest and easiest. Fairly safe vehicle. While it's the main angle, there are other applications that are possibly going to be presented for it, because they're not fast vehicles, but they can carry quite a lot. They can carry a couple of 100 kg relatively easily, because really just a parachute moving at a fairly modest speed. But the main thrust of it is recreational stuff. And many favoured flying areas are now populated. One of the best areas to fly was over in the, am I out of shot or anything, or does it matter?
Much better from this side.
Okay. One of the best places to fly is over in the western suburbs, west that way, western suburbs of Melbourne, around Sunbury, Werribee kind of area. It's flat, so it's easy to take off land. You've got fairly calm weather around in the early mornings, which is the best time to fly. And historically, those areas haven't been very well populated, but now they are. And people really don't like the sound of a two-stroke engine flying above their homes around about 6 in the morning. So if you've ever ridden a dirt bike, it sounds good when you're on the dirt bike, but it doesn't sound so good when somebody else is riding around on it. So that was their problem. So after about 26 years of development of petrol vehicles, it was time for them to join the electric revolution. And that's why they basically worked on the joint project with Swinburne, which is where we've been looking at doing an electrified version of one of those vehicles, which, as you can see, it's basically kind of like a gondola with a fan strapped to the back hanging from a parachute. It really is as complicated as that. And the focus of tonight's presentation is going to be on what we've learned and the experiences we've had going through the process of electrifying one of these vehicles. So I can give us another space bar. Okay, so what I'm going to do is first talk about the design approach that we used and what this revealed about actually electrifying electric vehicles. I'm then going to go over the basics of the key technologies that we used. So that was the motors, the propellers, and the aerofoils, and the basic aerodynamics of the aerofoil. Once I've done that, I'm going to, and that'll sort of get us to a stage where it's, all right, we understand the key characteristics of each component, what is known, what isn't known. And then from that, I'll present the basic model that was chosen and the rationale behind that based on what we've already presented. Then I'll go over the analytical model that was developed and used, and then I'll talk about what was found from that, and I'll just sort of finish off with where we are at now, because I haven't finished the project yet, it is ongoing. And then after that, I want to have discussion, questions, comments, suggestions, things like that. It's a pretty smart group here and it's pretty well informed. So I'd rather think of it as more of a discussion than just like a Q&A time. So, design approach. In a simple world, this is how we would have designed it. We would have researched the properties of the key components, focusing on the characteristics and their availability. We then would have made a general design decision, basically saying these are the motors and propellers and parafoil that will work and are available. Let's design something that takes advantage of these and we'd be away. We make the general design, we model it mathematically to just sort of tune it a bit to get the specifics. Then you can say, right, now we know exactly what kind of, we know what's available specifically, we know what we can do with it, and then we just do a little bit of experimentation to fill in any gaps that might be there. So ideally, you just follow that linear path. Then you'd find that they'd build the final design and you'd evaluate it. You wouldn't have to test it. You'd only be evaluating it because you'd be that confident in what you'd actually done. So that's what we would have liked it to have been. I wasn't expecting it to be quite that simple, but I wasn't quite expecting it to be as convoluted as it did turn out to be, and I'll go into that a little bit more later on. But what really happened is it was something more like this. And this is actually more representative of what the real world is like anyway. It's just that I'll explain, I've probably been a little bit too generous, I'm not generous enough with the smaller arrows, but basically we researched the components, we came up with the general design, and then we realized there were a few extra questions, so we went back and did a bit more research. Then we went forward again, then we modeled to specify, then that raised questions, we had to go back a little bit. So we're kind of always going in that direction until you eventually end up with something you can build and evaluate. And usually you're going forward a lot more than you're going backwards. There were a few times when I felt as though I was going backwards a bit more often than I was going forwards. So this is actually really what did happen. But in the process of doing that, I did actually find a few things that were interesting about the development of electric aerial vehicles. And one thing that's, and what we found is primarily, it's not really that different from doing any other electric vehicle. We really had to squeeze as much as we could out of the existing technology, much like all EVs, and we still had to make a few custom components to bring standard parts together, which is much like a lot of the EV stuff that's done here. So even though it's aerial vehicles, the general sort of technical skill base you need is pretty much the same if you're doing any other kind of electric vehicle. Some examples though, with the first one was that Aerochute historically had been able to, they didn't have enough thrust, they could put a bigger propeller on it. If they still didn't have enough thrust, then they'd put a bigger engine in there. And you could get away with that because you still had a fairly small fuel tank, the weight didn't go up that much, and you'd be away. Whereas in this instance, if we get our, if we don't quite match our propellers to our motors, whereas Aerochute just kind of like went bigger and bigger until it worked, if we don't quite match it, we're wasting energy. You know, our motors aren't operating at their most efficient point. The propellers themselves might not be operating at their most efficient point. And then you need a lot more battery capacity, which then really puts your weight up, which then means you need a lot more thrust again, which means sort of back to where you started. So we really had to think carefully about how we're going to put everything together. We had to sort of select everything and match it accurately. And then on top of that, we had to think, well, hang on, maybe we actually need to stop making some assumptions about the basic architecture to actually squeeze a little bit more out of it again. And I'll go on that one later on. I'll go into this a bit more later on. I was actually quite impressed with some of the standard parts that we can get. We really just had to make gearbox housings to house our gears. If anybody's heard of a company called Small Parts and Bearings, pretty much any gear you want, they had the bearings. There were a lot of motor suppliers out there. There was a lot of standard stuff that we could just get. And it was really just a case of making brackets and things like that to bring the rest of it together. Let's go on the next one. So what I'm going to do is I'm going to sort of talk about what we ended up selecting just out of interest and the kinds of things that we found along the way as we did that. So we found a company called KDE Direct. They're the motors that they make, and that's the motor that we chose, the 700XF495 HP. It's basically a remote control. It's a motor for remote control applications. What we knew about it was that it basically had a maximum power of around 10 kilowatts. We had part of the torque curve. We knew what the torque was between 9,400 RPM and 11,000 RPM, but the producer of the motor didn't actually have a dyno that was capable of measuring at the lower RPM and the higher torques. So they were extrapolating from smaller motors up to the power for their larger motors. So we didn't know exactly what the torque curve was like, but we did still know the basic shape because it was a brushless DC AC type motor, and therefore we were able to find journal articles on similar motors, and we could see what the basic shape of the torque curve was. So we also knew what their peak efficiency was. So we had kind of like half of the torque curve. We knew a fair bit about the motor, but not everything. What we didn't know though was the complete torque curve, and that's really what we needed. So what we did is we did a stall torque test. We just basically put a bar on the motor, tightened it up, put a spring balance on the end, and then just quickly gave it full power before things got too hot. A little bit of smoke came out, but not enough to cause any major damage. And then we just quickly measured the force on the end of the bar. We had our stall torque with the rest of the curve and the maximum power. We were able to estimate the curve that we had. So once again, so what this means is that we didn't know everything, but we were able to get a slightly better picture so that we could make more informed decisions, but we still weren't 100% confident. But that's basically where we were with the motors. Next one. Propellers. This one actually did my head in a bit. What we do know about propellers has basically been known since around about World War II. Okay, and every propeller, not even just any specific propeller, but a family of propellers can be defined by a chart like this. What we have down the bottom is something called the advance ratio, which is the velocity that the propeller is moving through the air divided by the rotational speed and its diameter. Okay, and that's a dimensionless ratio. And when you get the horizontal axis, you can then get the coefficient of the coefficient of thrust and the coefficient of power and the efficiency. And you can do this for basically, you can get a propeller kind of that size, you can test it, and that graph will still hold for propeller this size, or this size, as long as the geometry basically stays the same. Okay, so we knew the propellers could be well defined. There was a lot of understanding of propellers from this perspective, how to define propellers, how propellers behave. So we knew that there was a basic theoretical model that we could utilize for modeling. However, there was stuff that we didn't know. Oh, sorry, there's still more that we knew. So we also know that propellers cause swirl, and they also cause centrifugal effects. So if you take a look at that diagram there, you've basically got fluid coming in. This is obviously a simulation. It's representative of what happens in reality. Your air comes in relatively straight, but then when it leaves, there's a bit of swirl, and there's also, it gets thrown out a little bit because as you can imagine, don't ask me why I'm using chewing gum, I just am. If you stuck some chewing gum on a propeller and you spun it up, that chewing gum would eventually come off, and it's not going to go backwards, it's kind of more or less fly out. It's like a centrifugal effect. So that happens to the air as well. So as the air goes through the propeller, some of it gets thrown out, and some of it gets a swirl. The majority of it certainly goes in the direction you want, but there is a bit of swirl, and there's a bit of some centrifugal effect as well. And that's basically wasted energy. That's something else we know about propellers.
That's why you have a cowl around the propeller and boat back.
So that can help, yep. And what we also know is that they run much better in a free stream. This is more of a close-up of what some of the aerochutes look like. You can see that the propeller is put behind where the pilot and the passenger sit. So on that one, maybe not so much, but on some of the others where you've got two seats, about a third of the propeller is basically blocked. Okay, one, that means your propeller's not working, you're not using the area as much as you could, but also the flow coming in is no longer straight. You know, it's tumbling in, it's got some turbulence, and these things can really muck up your thrust. If anybody's seen it, it's, I think Volvo, I'm pretty sure it was Volvo, they made a unit where the propeller on it was basically an outboard engine, but it was spun around so that the propeller was facing the other direction, and therefore it wasn't being affected by the, you should call it turret, that the propeller was mounted on. It had free flow coming straight into it, and the performance increase was quite considerable. You know, you just need something small to disturb the flow, and your propeller doesn't work anywhere near as well as it does. I remember we had a speedboat, and my brother was working on it, and there was a small nick in the propeller, and we just weren't getting as much performance as we thought. Oh, maybe it's the nick, couldn't be, it's that small. But it actually was, there was enough to disturb the flow to really disrupt the way the propeller worked. So having something in front of it is also going to do a lot to inhibit the performance of your propeller. So this is the propeller we ended up choosing. The biggest piece of information that we didn't have was the specific properties of the propeller. When we contacted the suppliers, I'm not sure if they were acting dumb or not, but they just like, we don't have that. Yeah, we don't do that. And I've spoken to some people in the model area, because once again, this was a remote control application. And they said basically they have like a shed full of propellers. They just take a propeller off, they put it on that plane, and if it doesn't work, they'll take it off, try another one, another one, another one. That seems to be the way they work. So I think when I asked the question, do you have a coefficient of thrust and a coefficient of power versus the advance ratio, I got the feeling we were the first people who ever asked them that, because nobody else had sort of thought that way. So, but what we could find is we could find information on propellers that were sort of had a similar pitch, but they weren't exactly the same. So we basically found some propellers that were bigger, some propellers that were smaller, but had those graphs. And so then what we did is we used those graphs to kind of average out what we thought this propeller might have behaved like. So that was why we sort of filled that gap. So once again, it was reasonably informed, but we still had to do the best with what we actually had. Next. Parafoils and aerodynamics. What we did basically know is that they're called parafoils. Some people call them parachutes. I don't really care what you call it. Some people probably get upset, but I don't care. They basically act like a wing. And there was quite a lot of information in the literature, in aerodynamics literature, on the coefficient of lift and the coefficient of drag, given the angle of the chute. So it was actually quite easy to get a model for what kind of lift and drag we could expect from the parafoils. We didn't have data on the specific one because that's made by Aerochute, and Aerochute, while they make them, haven't actually run the experiments to get that kind of data, but the profiles were pretty similar. And therefore we felt pretty confident that we at least knew these ones fairly well. And this is what we basically came up with. So remember when we first spoke about how you get a bit of swirl? One of the tricks for dealing with that is to have one propeller spinning one way, and then just behind it, have another propeller spinning the opposite way. So one gives you swirl in one direction, the other one basically captures that swirl, turns it the other way, and converts it back into thrust. So at the end of having a counter-rotating system, you don't have swirl. So that means we're going to get some more efficiency there, where everything's going to be going to thrust. Secondly, as somebody pointed out, stole my thunder a bit, but yes, that's all right. We've got a cowling around there as well to sort of inhibit the centrifugal effect. So any air that tries to come out is basically going to get caught up in the free stream velocity, go out the back, and once again, we've captured a bit of extra energy there. We've also put it on the side. Our side-mounted RC props and RC motors. And by putting it on the side, we've got free stream coming in. Okay, so we no longer have a disturbed flow. As you can see, that's a double seater. And so that had the propeller behind it, that flow would have been disturbed quite a lot. So these are all sort of smallish things we've done so that we could squeeze as much out of it as we could. Early on, we realized we should go counter-rotating props and we should go side mounting. The reason why we then went for that kind of size was that was basically the biggest remote control props we could find. So I've ended up with that, like I said, basically gone down the RC path. What we needed to do now, though, was actually model it so that we could make sure that we had the right ratio between the motor and the gearbox, and also to make sure that we would actually have the kind of acceleration we wanted in the vehicle static thrust, and that we'd actually get the maximum speed we'd want. Next slide, thanks, Bill. So this is a diagrammatic representation of what the mathematical model was that we set up. So we started off by first of all specifying rotational and vehicle velocity. So it's the speed of the propeller spinning, and it's the speed that the vehicle's traveling at. So from that we could work out the advance ratio, and then using that graph I showed you earlier of the coefficient of power and the coefficient of thrust, we could work out the power and thrust. By taking a look at the properties of the parafoil, we could work out the vehicle drag. If we then if we subtract the drag from the thrust, we get the net force that's basically being applied to the vehicle. We then take the battery capacity. If we divide the power into the battery capacity, we then get our flight period. We were looking around 30 minutes. Aerochute basically said people like to fly for about 30 minutes. The battery capacity then influences the mass. We divide that into the net force, we get our acceleration. So what we were then able to do is we could keep on playing around with the rotational speed and vehicle speed, make sure that the power we got was acceptable, that the motors could produce that power, that it would give us a reasonable flight period, that we had enough batteries, put that in the mass, and then find the point where our acceleration basically tapered off to 0, and we wanted that to be around about 60 kilometers per hour. So by using this basic model, we were able to tune the specifications for things such to match the rotational speed of the propeller to the rotational speed of the motor, make sure we had the right power, enough battery capacity, and basically we did enough to tune this tune the model as effectively as we could before we actually launched. And that's probably pretty good design practice anyway. Mario is an example of that, where I might get these numbers wrong. You predicted 85 kilometers and you got 84 kilometers, is that right? Yeah. And that's the kind of accuracy you can get if you model these things correctly, and if you know enough information about the things you're dealing with. Just tap again. So, and this is just what it looked like in Excel. And we use that to find the gearbox ratio and verify flying time. So, sort of that diagram you saw earlier has basically been expressed mathematically in this spreadsheet. There we go. So, what was found? So far we can say it is viable. It really should have been easier to do than it was. The suppliers are a little bit unsophisticated, and to be honest with you, I'm still a little bit suspicious about that propeller. I am thinking that maybe that propeller is just not as refined as it could be. It's probably a perfectly good propeller for its application. As I've been testing it more, I've just got this bad feeling that it's going to end up being not as efficient as I was assuming it was. But remote control stuff has really come a long way. It's something they call the hummingbird effect. If we tried to do this, say, 10 years ago, I don't think it would have just been battery technology holding us back. I think it would have also been the technology in the remote control industry. What I've learned now about remote control is, despite the fact that I don't see a huge amount of sophistication, because they're working on things so small, it's very easy for them to make and test, make and test, make and test, make and test. Relatively speaking, they've got pretty large R&D budgets. And so there's a lot of motor technology out there, motor controller technology and propeller technology that we were able to utilize. And that was just something that really did save us. And like all EV projects, like I was saying earlier, you really do need to squeeze everything. And that's basic, and it looks like that's just going to be true of all EV projects at the moment, until I get like something like fuel cells working, or metal air batteries, which are practically fuel cells anyway, working. We are probably going to have to squeeze as much as we can out of everything. All right, so where are we at now? So we're on the second propulsion unit iteration. So basically the information we got on the propeller wasn't quite right. We were able to get a curve of rotational speed versus static thrust, and we got a curve there, and we were getting close to the thrust we needed. We need 25 kilograms per unit. We weren't getting that. We're actually a bit under, to suggest throughout our speed was up by about 30%. So we're going for the second iteration. The curve at least looked as though it was going to give us the thrust that we need, as long as we can go further. So things didn't work out quite as nice as we'd hoped. We have burned out a motor. I used to work for Davey Water Products, or Davey Pumps, as you know them, and all our motors, we basically put thermal protection in there. So when I was testing this motor, I was just assuming, I was sort of thinking, implicitly assuming every motor would come with thermal protection. Surely they don't. Luckily, there wasn't enough smoke for the fire department to come around. That would be the second time the fire department's come to the electric vehicle laboratory at Swinburne, so I'm glad it's still only one. $3,000. Yeah, well, they're just across the road. Yeah, so they don't have far to come. It's well lined up. Yeah. We have actually done some thrust testing. So if you click on that, Paul, so click back. You know, go back to. And when this first started, I could really hear the gear whine, and I was getting a little bit worried. But pretty soon, you get the propeller bars overcoming that. I don't know about you, but I quite like that noise.
Does that have a reduction ratio on the motor?
That one does. That particular one had a reduction of about 2.6 to 1, I think it was. And that was a planetary gear system. But it now looks as though we should probably have a ratio of about 2 to 1. So we just got standard spur gear reduction. And to get the torque, it's looking like we'll have to have 2 motors per system. That's why I burned out the first motor.
Like one on the front, one on the back?
Either side by side.
Okay.
Yeah.
What RPM do you go there?
Oh, I I think we got up to around about, 3,000 RPM.
Yeah, I don't know, since
Something. Oh, you're talking about the motor, or you're talking about the propeller? Oh, yeah, it was something like that, I think. And when we ran that one, I think we went a bit faster. I'm trying to remember the specifics, but we basically, the motor went to its maximum speed, very little current was being drawn. So we realized that at least the motor there wasn't as much power going to that system as what we'd anticipated, which basically meant the propeller was designed for a higher speed than what we inferred from the data we'd interpolated between earlier on. And that was actually, after this, we were lucky enough to find another supplier of these propellers, and he confirmed that the thrust we wanted was perfectly viable, but we probably did have to go a bit faster. So it's good to get some independent verification on that. But once again, we did a number of runs at different RPM, measured the thrust. That's the scales down between my legs. You can see that's basically how we set it up. And it looks as though, yeah, we should be able to get that. It's just part of, you've got to do some testing.
Yeah, so you're just doing it with DLL, using VSDs, right?
So yeah?
You're doing it with DLL with it, basically.
What do you mean, sir?
Just basically just kicking it.
Well, we kind of thought about it beforehand.
Yeah.
There was a bit of prior thought.
In terms of the starter control.
So, yeah, what do you mean, sir?
As opposed to the direct online, you have to speed control.
Oh yeah, we've got an Arduino hooked up to it too. So you got a controller hooked up to control. Sorry, no nonsense. Those motors come with off-the-shelf controllers.
Yeah.
We just fed a signal via an Arduino,
yeah,
and then we edged it up sort of manually. Yeah. So yeah, next slide. And so yeah, discussion time. Any sort of questions or comments about? Yep.
Two things come to mind. One, you say that the figures that you have are based on the geometry of the propellers you have.
Yep. We'll tap back and we'll just get that one up so we're all on the same. You're talking about like those graphs we had?
Two things come to mind with that. One, the availability of the propellers.
Forward. Yep.
Seeing as you're buying stuff that is commercially available somewhere, that it strikes me as a limiting factor.
That's probably something I should have said earlier, in that one of the constraints of the project is that we are trying to make something that Aerochute can produce. Aerochute assembles these assemblies. They don't make their own propellers. They don't make their own motors. They don't make controllers. So one of the constraints is we do have to use off-the-shelf componentry. So that was a constraint that we definitely had, yes.
It definitely strikes me as being a limitation, because if you were able to make a propeller,
why is the limitation that it is? You said they're pretty much digitized the way these things work.
well, yes, but if you change the geometry of the propeller, for example, if you use a 3-blade top instead of a 2, it would change the outcome. If you were able to make something that was tailored exactly to what you needed, rather than relying on what was available.
You could probably squeeze a little bit more out of it. I'm hoping, remember when I said I'm a bit suspicious about the propeller? If it turns out to have a lower efficiency than I'd assumed, then definitely it is, we've really got a problem. If it turns out that they are at least reasonably efficient, and we can say, okay, we have to make a gearbox to match the motor to the propeller. I mean, it's one of those things you have to do anyway. Certainly in an ideal world, we'd do everything ourselves. But yeah, I guess it's kind of making that choice. Do we really want to put the effort into that, or are we happy to leverage other people's expertise? We've decided to leverage other people's expertise. If these were big selling units, and in the future, I'm hoping these take off. When I've given this presentation before at other places, I've seen hands shoot up, and there were people who were ultralight pilots, and they would like to use these units on their ultralights as well. So I can see some other commercial applications. Once Aerochute gets this up and running, I can see them selling these units to other companies. If they go down that path where they're really putting a lot of them out, then they might say, you know, maybe it is worth employing an aerodynamicist to actually sit down, do the computational fluid dynamics, and design a custom propeller for us. Yeah. And if and it would be a very good news story if it turns out to be that successful and they can go down that path.
Well, there's certainly an aspect that I'm interested in.
Right.
So obviously,
this whole project sort of mirrors areas of interest.
Gotcha. Yeah, we'll certainly watch this space, and hopefully it does. Yeah, take off. Yeah.
From
From a different point of view,
Yep.
I've been pilot flying for 40 years, including paragliders. Will a single-seater version be foot launchable, or will that be too heavy?
A single, if we get 100 kilograms of thrust at the start, we should be able to launch a two-seater based on the experience of, and once again, I'm relying on Aerochute's expertise there. They said if you can give us 100 kilograms of static thrust, that will inflate the parachute behind, and that should be enough to get them off the ground. And that's all they've really told me. So that's the goal that we're pushing for. Yeah. Sorry.
I have a silly question. But, I understand you were building a model of the thing before you got full-size screen.
Say that again?
Did you say you were building a model of this before you got full-size screen?
No, we'll build the full-size one straight away.
Right.
Yep. But we're just building, we had I guess you'd say an analytical model. Yep. Yep. Mathematical one. Sure, no worries. Start at the back and we'll work our way across. David.
How do you do your contra rotation?
Fortunately, this is what one of the suppliers has told me, and my faith in suppliers has been shaken slightly lately. But one of the suppliers told me that they do have basically a reverse propeller that's designed to spin in the opposite direction. So we'll just buy an inverted one, and we'll just have the, we could swap the polarities on two of the phases to have it going the other direction, or we could turn the unit around or something like that. So yeah, as long as we get a propeller that's designed to spin the other way, we're pretty much set.
Two motors, one behind each other.
We've sort of made it modular, and you've got like basically a propulsion unit. So we'll put one propulsion unit in that way, we'll put the other one in that way, or we're spinning the other direction, we should be there. So that's the plan. And I'll have to check that email out, maybe email that guy again just to double check that you do seriously have one that goes the other way. Otherwise, we're going to have to do some 3D scanning and some mirroring in CAD and some rapid prototyping. Yep.
Did you try spinning up a standard paramotor size prop first and dismiss that? Or why have you gone?
Because they were so large, you're talking about the ones that are currently used on the Aerochutes?
Yeah.
Yeah, so Aerochute had done some work with that, and they were just finding it hard to get a motor of the right size that was still affordable to power that size propeller.
The budget limitations there.
I guess so. Also just availability. I guess, and this is actually something I've noticed a while back, cars are probably one of the hardest things to convert to electric because for one reason or another, motors of that size, they're just not commonly available. When you get down to this smaller scale, we're leveraging off the remote control community. We just got on internet, did a search, and we found a choice of motors. When I spoke to Crown coaches who were doing their buses, they just got a standard large-scale industrial electric induction motor and threw it in the back of a bus. As soon as you get to a car, it's really hard to find an existing application with motors of the size you want. And that was what Aerochute found as well. It was hard to find motors that were just sort of right power-wise for what they wanted. If the speed was different, they could have just put a reduction on there, but they couldn't get quite the right motor. So they'd already tried that. We also decided that we should go to the side units to get better flow, and their propellers are much larger. And so if you had these massive propellers on the side, I mean, even if we tap back a bit to the basic design that we've got. No, I was going to show the other way. Sorry about that one. There we go. Right, back one. They're looking pretty big. Even like at first you go, ooh, but it kind of grows on you. But I think if you had the standard size propellers on the side, and you still want them on the side for the extra efficiency, it'd just look a bit ridiculous. Yeah. And also there'd be issues where these are usually put on a trailer and towed around. So like this, I think you can put them on the trailer, or you can turn them around, or we could even make them detachable. They're reasonably easy to handle. Yep. Oh, yeah, sir.
So you're testing, you're doing a real life prototype.
Mm-hmm.
You're going to take it up and test it.
I'm not, but
pilot with a pilot.
I'm not with me. The pilot can do it. Yeah. No, I have complete faith in my design work. I'm just not going up.
There's no stage between. There's no stage between engineering and prototyping.
Say again?
There's no stage between engineering and prototyping. You're not doing an intermediate step or something like that.
Well, I guess it's testing those propulsion units. Like we're making sure each unit gives us that static thrust first.
But then you go straight to the flight.
Yeah. Well, what we'll do is once we do a static thrust test on one of them, what we will then do is we'll put them onto a unit and we'll do a static thrust test on the unit. We won't actually fly it just yet. You could always just sit it there and run it for a while. One of the good things about the Aerochutes is that if you lose power, you've already got your parachute. You just,
I mean, he's probably not pretty skilled. Oh, this guy's good.
I'm sure they are. Yeah, I trust them completely.
Well, they're on state.
Yeah. So no, there's when we looked at it, there wasn't really a strong argument for anything sort of
Well, you can't
in
really
between.
simulate it.
They have had requests, and this is a bit of a tangent,
Yeah.
but they have had requests from the Singaporean military to have an autonomous version. I think it was, and somebody wanted an autonomous version actually. It might not have been Singapore. The idea was that because these units are fairly cheap and have a phenomenal load carrying capacity, you could send it to a place where people were stuck, stranded, and you could just drop supplies, and you don't care if the aerochute gets left there because it's relatively cheap.
Yeah.
So if the autonomous version happened to take off beforehand, you could always put the control system on it and test it autonomously.
Commercial value.
Oh, but what I get is if you wanted to test it before you strap some human being into it, and you don't have the time to train a chimpanzee, yeah. So, yeah.
Just a quick basic question. If you lose thrust on one side, they sort of need to be yaw around.
I don't know if it'll happen immediately, but you're not the first person to mention that one. We are looking at having a master control system.
So you can just switch.
You can do that. But at the same time, we spoke to Aerochute about that. You can steer these devices anyway. So if you've got thrust on one side, you could steer it to sort of get yourself home. So in a sense, you've got some extra redundancy. Or you could just sort of kill the power. The other concern we've got is maybe even if you don't lose a whole side, you just lose half a side or something like that. So there might be a control system on there, whereas if the current dies to one, it just kills all the others. That's the kind of thing we can start talking to Aerochute about what they would rather have happen.
There's nothing to be gained with doing testing, is it?
Probably not a huge amount. Wind tunnels are pretty expensive. Yeah, wind tunnels are expensive compared to the cost of just making one and trying to fly it.
You have to fly it to generate the fly, so it's not.
Yeah.
What is the top speed you're aiming for?
60 kilometers an hour. That's the nominal speed that these things usually fly at.
They just put it on a ute or something.
Well, you could do. We were talking about, we needed some data on the parafoil. Before we started doing our literature review, we didn't have that data, and we're thinking maybe we should even get one of the parachutes, weigh a trailer down, tie something to it, get a spring balance, measure the angle and things like that. But then we found that data and we didn't need to. But you could conceivably do that, yeah.
I reckon it's up.
Okay.
Each the legs.
Oh, yeah.
This weekend. Done. Looks like that wraps it up.
Looks like they're done.
Yeah. Thank you, everyone. Sorry? Oh, sooner the better. Yeah.
Clint, have we got access to the tea room?
I can let you in.
You think